If you've spent any time exploring physics on the internet, you've probably encountered the idea that higher dimensions are gateways to alternate realities. The pitch is usually that if you can just access the fifth, sixth, or 10th dimension, you step into a multiverse where any timeline and any choice is possible. Viral explainer videos often map these out like a series of branching paths. They claim the fifth dimension is a plane of alternate worlds slightly different from our own, and by the time you reach the 10th dimension, they describe a realm where all physical constants can be rewritten at will. Talk to an actual theoretical physicist about these videos, and you will usually get a heavy sigh. In the physics community, these pop culture explanations are notorious examples of pseudoscience. The error in the viral model is how it treats the concept of a dimension. It takes ideas like probability, human choices, and alternate timelines, and tries to force them into slots that are strictly reserved for spatial geometry. This creates a trade-off. You can keep the narrative framework of the sci-fi multiverse, or you can discard it to look at how the physical universe is actually modeled in research. This diagram shows what a dimension is in theoretical physics. It is a simple mathematical degree of freedom. It's a coordinate axis used to locate a point. You have an x-axis for length, a y-axis for height, and a z-axis for depth. Tracking where that point exists in a given moment adds a fourth axis for time. Notice how strict this definition is. A dimension is a physical measurement of space or time. It is a direction you can move in, or a duration you can measure. There is no axis for probability, and no coordinate plane for alternate life choices. That doesn't mean we are limited to calculating only what we can see. Mathematicians work with spaces far beyond our biological perception. Data scientists regularly use 9-dimensional geometric lattices to organize complex datasets, mapping out abstract shapes like a 9-cube. But those higher dimensional structures remain abstract math until theoretical physicists attempt to map them onto the physical fabric of the universe. Adopting this definition narrows your focus. You lose the narrative flexibility of the sci-fi model, but you gain a vocabulary that matches the way physicists actually calculate space. This brings us to string theory. It attempts to unify the physics of the very large, gravity, with the physics of the very small, quantum mechanics. This model replaces point particles with microscopic vibrating strands of energy. The problem arises when physicists try to calculate this unification using only our standard 3 dimensions of space. The equations immediately break down. This image displays the kind of mathematical frameworks required to evaluate these theories. When you run the numbers for a string tracing its path through standard spacetime, impossible mathematical contradictions emerge. These are known as quantum anomalies, and they ruin the theory unless a specific variable, called the central charge, is perfectly balanced. To fix these broken equations and clear out the anomalies, physicists can't change the behavior of the strings. The only option they have is to mathematically extend the coordinate frame itself, adding extra degrees of freedom to give the equations room to resolve. When you calculate the anomaly for the quantum string, the math perfectly balances only when the equations are run using exactly 9 spatial dimensions plus 1 dimension of time. This specific requirement stems from supersymmetry, a theoretical framework necessary to account for both the matter and the forces we observe. It relies on these extra spatial axes to keep the math consistent. In this framework, 10 dimensions aren't a creative choice. They are a requirement for the math to be self-consistent. Without them, this specific attempt to unify gravity and quantum mechanics produces impossible results. That creates a contradiction. The math of the theory demands 9 dimensions of space, yet human beings only experience 3. This animated grid illustrates a mechanism known as compactification, which physicists use to explain where those extra dimensions went in the context of the Big Bang. The theory suggests that while our familiar 3 dimensions of space expanded outward to form the universe we see today, the remaining 6 spatial dimensions stayed stunted. They never grew. Instead, these 6 extra dimensions folded up into microscopic, complex geometric structures. These are often modeled as Calabi-Yau manifolds, locking the extra degrees of freedom into tight mathematical configurations at every single point in space. The scale of these folded dimensions is almost impossible to picture. They are estimated to be 1/billionth of a trillionth of a centimeter wide. If this theory is correct, these 6 extra dimensions are everywhere. They are constantly woven into the fabric of space all around us, but they are simply too small for human perception to ever interact with. Looking at this photograph of distant galaxies, it's easy to see why standard astronomy won't help us here. Telescopes look across the vastness of the observable universe, but they can't detect something compacted down to the subatomic scale. To prove string theory, we must probe physics at energy scales far beyond our normal biological limits, smashing particles together to see if any energy interacts with those hidden dimensions. This requires massive machinery. Facilities like the Large Hadron Collider represent the engineering currently required to test the boundaries of standard particle physics. Inside these detectors, physicists monitor high-energy collisions, hunting for missing energy or signatures that might suggest a particle briefly entered an extra-spatial dimension. Because these dimensions are so small, string theory remains an elegant mathematical model that is currently impossible to verify with experimental technology. This alignment scorecard shows the choice you have in understanding dimensions. You can align with either the narrative model or the physics model. The pop science narrative model is useful if your goal is to enjoy science fiction or engage in philosophical thought experiments about alternate histories. But the cost of this model is that it doesn't translate to real research. If you view dimensions as timelines, you won't be able to engage with actual particle physics or quantum mechanics. Adopting the physics model means aligning your worldview with the math being used to reconcile general relativity with quantum mechanics. The trade-off here is that you must accept a universe that operates on geometric rules that the human brain is physically incapable of accurately picturing. This grid represents how higher dimensions are modeled as purely spatial geometries. They are devoid of human choices, time travel, or alternate versions of yourself. The choice is between an intuitive fantasy and a rigorous, invisible, and highly complex mathematical framework. Choosing the physics model means accepting that our attempts to explain the universe rely on a geometry we can calculate. For nearly a century, physics has relied on two separate rulebooks to explain the universe. We use general relativity to track massive objects like planets and galaxies, and quantum mechanics to map the subatomic behavior of atoms and light. Both work perfectly on their own, but when extreme phenomena, like the crushing center of a black hole, force these two systems to combine, the math catches fire. The equations break down and produce impossible answers. The core of this mathematical failure comes down to a single geometric assumption: the idea that fundamental particles like electrons and quarks are points with absolute zero size and zero volume. This graph illustrates the problem. When two-point particles interact, all of their energy is crammed into a single location with zero space. Because dividing any amount of energy by zero mathematically guarantees an infinite result, the calculation blows up. This persistent infinite error is the single biggest unsolved roadblock in physics. It proves that our model of reality contains a structural failure. In the late 1960s, physicists proposed a radical workaround. Instead of treating particles as zero-size dots, they replaced them with one-dimensional, microscopic vibrating loops. Giving the particle length changes the math of a collision. When two strings interact, they don't crash into a single point. They merge seamlessly. On the data curve, energy spreads over a stretched region, keeping the calculations finite and manageable. This geometric adjustment allows gravity and quantum mechanics to finally exist within the same mathematical framework. While strings repair the math, adopting them forces physicists to accept a different architecture for the universe. In string theory, every particle is actually the exact same type of string, just vibrating in a different pattern. The specific energy of a string's vibration dictates its mass and charge. Pluck it gently, and the low energy wave produces a lightweight electron. If it shifts to a frantic, high-frequency wave, it becomes a heavy quark. To account for all the varied particles we observe in nature, these strings need room to produce highly complex, multi-directional vibrations. Calculating these vibrations in our familiar 4 dimensions, 3 of space and 1 of time, mathematically suffocates the strings. The restricted space produces fatal quantum anomalies, spitting out negative probabilities that have no physical meaning. To balance the equations and cancel these anomalies, the math dictates that the universe must possess exactly 10 dimensions. That poses an obvious contradiction. If the math requires 10 dimensions, why do we only experience 4? Theorists propose that the missing 6 dimensions are compactified. They are curled up so tightly that they remain invisible, hiding inside every single point of our 3D space. These curled-up dimensions fold into complex six-dimensional geometric structures called Calabi-Yau manifolds. Strings are forced to move and wrap around the intricate topology of these shapes. The holes, curves, and intersections act as rigid physical constraints. Because the shape restricts exactly how the string can vibrate, the geometry itself determines the masses of the particles and the strengths of the fundamental forces. The constants governing our universe are not random. They are the direct mechanical output of hidden microscopic geometry. Since a Calabi-Yau manifold's geometry dictates our specific physics, identifying exactly which shape our universe actually possesses is the central problem. But the equations do not point to one single, elegant shape. Instead, the math allows for an estimated 10 to the power of 500 possible valid Calabi-Yau geometries. Each of those specific shapes would produce a completely different universe. Some would have crushing gravity, some would lack light, others would be void of chemistry. Physicists call this the string theory landscape. Rather than predicting the exact laws of our reality, the theory provides a framework for an almost infinite multiverse of possible physical laws. Because the math can accommodate practically any universe, it struggles to make unique, testable predictions about the one we actually inhabit. Directly proving the theory is effectively impossible. A string is so small that a particle accelerator powerful enough to see one would need to be the size of the Milky Way galaxy. Even our most advanced engineering projects are millions of times too weak to reach the necessary energy scales to probe a string directly. Physicists search instead for evidence of energy leaking out of our observable space and into these hidden dimensions during high-speed particle collisions. Scientists also study this, the cosmic microwave background, the oldest light in the universe. They search these ancient heat maps for hidden polarization patterns left over from the Big Bang. String theory succeeded in putting gravity and quantum mechanics into the same mathematical room, revealing a vision where matter is music and physics is geometry. But it leaves us staring out into an endless landscape, searching for the exact shape of our existence.